Very much. Thank you very much. So this is a joint work with colleagues from University of Central Florida and University of Wisconsin-Whitewater. And sorry, but I will start with some stuff that I believe most of you know very well. Just very quick pass over those things. So this is about something, the text indexing. You know, we have a pattern, and what we would like to do is we would like to find all occurrences of a queried pattern on a target text. And for this thing, to make this thing fast, we have the indices, and the basic indices, the basic data structures we use are the suffix trees, suffix arrays, and finally the Burrows-Wheeler transform and the FM index. You know the suffix trees, so given the text, what we do is we just take all of its suffixes and insert them into a tree. So we have the suffix tree. So we know that if a pattern appears in a text T, it should be a prefix of a suffix. So what we do is we start from the root node of the tree. So travel with the queried pattern on the tree. If at the end we are still on the tree, then this means that the pattern appears on the text, and we can just find the locations by finding the leaf nodes originating from the point that we are currently on. So the bad side of the suffix trees was their sizes. Although it's a linear space in theory, it's an ON data structure. However, in practice, the hidden constant is around 15 to 20, which means if you just index 1 gigabyte of text with the suffix tree, most probably you will have 15 to 20 gigabytes. So this was a huge cost. So in the 90s, there is a solution. Instead of the suffix trees, let's maintain the suffix arrays. Again, we have the suffixes, and what we do is we sort them, and actually we maintain an array which includes the starting position of each suffix in the lexicographical order. So on the suffix array, what we can do is we can imitate what we do on the suffix trees, perform efficient pattern matching by using some binary search and by the help of the LCP arrays, you know. So the good thing is now the hidden constant is around 4. So instead of having 15 gigabytes for 1 gigabyte, now we have 4 gigabytes for a corresponding text. So when compared with the suffix trees, surely this is a very advantageous case. However, soon after, in practice, we realized that it is still very high for, and is still a big price we pay. So compressing the suffix arrays, is it possible? So in 2000, Grossi and Witter answered this yes, and they just showed us how compressed suffix arrays can be maintained. So that is very nice. And in the same year, we have the FM index by Ferragina and Manzini. So we will be focusing on FM index. So what is an FM index? You have a text T and you take its Burrows-Wheeler transform. And Ferragina and Manzini just showed us that the Burrows-Wheeler transform can be used for efficient pattern matching. So that is very nice because the size of the Burrows-Wheeler transform of a text is compatible, is the same with its original size. It's analog sigma bits. So that is very good. And what else? So it is good for searching. However, for the locate queries, for reporting the occurrences, we still need the suffix array. So for the suffix array, instead of just maintaining the whole suffix array, which will take a huge space, what we do is we just sample it and use the sampling strategies that I will not go into detail, but most of us are very familiar with. So that is the FM index. So in this talk, in this study, what we consider is there is a text and there is an FM index constructed over this text. What we would like to do is we would like to search, we would like to find the values of the suffix array and also the inverse suffix array values of the reverse text. So is it possible to do it without using any additional space, just using the forward elements? And we answered this question positively within this study. And we simply show that the suffix array and the inverse suffix array values of a queried position can be obtained from the forward FM index proportional to the length of the shortest unique substring that starts at the target position. For instance, here, let's assume we are curious about some suffix array value, and at the end, this is the forward text and this is the reverse text, and we know that it will be somewhere here. So the amount of cost we will pay is proportional to the length of the string that is unique starting at position K in the reverse direction. In the forward direction, it is the length of the shortest unique substring ending at that position. Okay, so why we consider this? Why we consider this? Actually, this can be seen as a special instance of the relative FM index. Assume we have two texts which are very similar, and you have the FM index on the first one, and the second one differs at a very few positions when compared to the first one. So instead of creating a second FM index for this gentleman, what we do is we use the currently available FM index by creating the index on the new one. So that's the relative FM index. And actually what we are doing here is, yes, this is a relative FM index, but the second text is actually totally the reverse of the previous one. We know that certain text from both directions has applications and approximate pattern matching, but maybe the most important thing, application area that actually motivated us to focus on this problem originates from the DNA sequences. So you know the story for the DNA sequencing technology, the reads can come from the forward strand as well as the reverse strand. So we need to, while matching a read towards a reference genome or some target DNA sequence, we need to consider its reverse complement as well. To accommodate this, what we do in general is once given a DNA sequence, we append the reverse complement of this to the end and create the whole FM index on the double-sized sequence and then answer the questions. So that might be an opportunity for this study to reduce the space to half. Maybe not very soon, but just a starting point, let me say. So what else can be done? So compute, actually the Burrows-Wheeler transform of the reverse text has been previously mentioned, and computing this thing in parallel is an issue. So we can also speed up this parallel Burrows-Wheeler transform computation, particularly for the reverse text. Okay, so much talk, so let us focus on how we do it. Okay, so let me try to spend a little bit time on this thing. Okay, so assume we would like to find the reverse suffix array value 14, and we are given this text. Okay, so AATC, 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 GACG is my text. So the reverse text is actually shown here, and I would like to find the reverse suffix array position 14 from the forward element. On the forward elements, I have the Burrows-Wheeler transform, I have the suffix array, and I have the inverse suffix array. So we know that actually the suffix array and the inverse suffix array are not maintained as a whole, but they are maintained with sampling. But for the time being, let's assume we all have everything. Okay. So the first thing to start with is, what is suffix array 14? So it points to a suffix which is the 14th smallest suffix among all the suffixes. So suffix array 14 on the reverse text should be preceded by 13 other suffixes. So the question is, what is the first letter of this suffix? We know that on the Burrows-Wheeler transform of the forward text, we have the actual text positions. So finding the 14th smallest element on this Hull-Barrows-Wheeler transform range will give me the first symbol, first letter of the reverse suffix. So what we do is, starting with the complete range, we seek for the 14th smallest element, and we see that it is a G. Now the next thing is, since the suffix that I'm looking for starts with a G, then all the suffixes starting with A, C, and dollar should be less than my target suffix. They should be the preceding. So how many of them exist? Actually, I can count it. On this whole range, we make a quantile query and then say that, okay, give me the number of positions that are A's, C's, or dollars. So this gives us 12. Now I know that 12 of the suffixes start with something less than G, but I'm looking for the 14th one. So what I do is, on the Barrows-Wheeler transform, I go to the range of G suffixes. So this is the range such that on the forward text, these are just the preceding symbols of the suffixes starting with G. Okay, now I am here. But now on this new range, I'm not looking for the 14th smallest one because I know 12 of them are already detected. So I'm looking for the just second smallest one. Again, the same story. On this range, I check for the second smallest one and I see that it is a C. Now I know that the second letter of my reverse suffix is C. So notice that actually searching backwards on the forward text corresponds to searching forward on the backwards text. So a little bit complicated, but I guess you all get what I mean. Okay, C, and then I count how many of the items are less than C on this new range, and I see that all of them are C, so nothing contributes. Continue. Now I go to the range GC, which is here. I'm looking for, again, the second smallest one because I could not reduce it here. So the second smallest is T. So T is in hand, and how many of the items are less than T? There is only one, so I record it here. And then length to GCT. When I go to GCT, what I observe is my range on the BBT becomes singular, which means I just extracted a unique substring, So when I come to that position, I just stop. And I count, I accumulate the range count, okay? So not accumulating the range count, but I am at position 17 on the Barrows-Wheeler transform. So what I do is I go and check the suffix array 17. So it gives me 11. So I am at this 11th position. However, after moving how many letters? 3 letters. So I just added and -1. So this gives me the text position 13. And text position 13 on the forward text maps to the text position 4 on the reverse text. So now I am done. I can say that the suffix array 14 on the reverse text is equal to 4. So good. And what I have more is an example for the inverse suffix array. I will try to make this a little bit faster. Okay. Now we are curious about the inverse suffix array 4. So where we start, we say that, okay, position 4 on the reverse text maps to position 13 on the forward text. So where is this 14th? What is this letter? We assume that we do not have the text. So this is a self-index. So we have just BWT suffix array and the inverse suffix array. So to get the position of 14, what we do is on the inverse suffix array, let's check the position of 14, which gives us 5. And if we go to the Burrows-Wheeler transform 5th position, we see that, okay, this is G. So we start with G. And what we do is we will now again count on the whole BWT how many symbols are less than G. So we see that it is 12, and we continue. We again land on the G interval, and we see that the preceding one is a C with an LF mapping. How many of them are less than C? So nothing. Again, continue. So the next element is T. So we go to GCT interval. So we have the ATs. So this helps by 1. Actually, following the same story, what we arrive is actually 13 elements or smaller. So for the inverse suffix array 4, including itself, so this will correspond to 14. Okay, but notice that we are always passing through all the shortest unique substring path. Anyway, so these are the main methods we provide. So what is the complexity? As you already noticed, so what we have here, first of all, we need to repeat everything H times, where H is the length of the corresponding shortest unique substring. So at each step, we perform some operations on the Burrows-Wheeler transform, and we assume that the Burrows-Wheeler transform is implemented with a wavelet tree. So the cost comes the log time operations on this wavelet tree, and plus we need to access the forward suffix array or the inverse suffix array 1 time. So we also add this thing. Summing up, actually, the operations on the wavelet tree can be done with log sigma time, and accessing the suffix array value with the sampling strategies is log to the 1 plus epsilon n for small epsilon. And on the average, H can be expected to be logarithmic with base sigma to n. That's for sure with the assumption that this text is independently identically distributed, which is never, which is very rare to come up with. So we have some experimental comparison as well. In the following slides, we will see that. But if we combine all these things, we see that we can extract the suffix array and the inverse suffix array of the reverse text in time log to the 1 plus sigma to n for some small epsilon values. For the space complexity, we are not using any additional space. So we reach this result without using any additional space. So as I mentioned, to see its real performance, what we did is some number of experiments. We implemented the scheme with the SDSL Lite framework, and we tested it on the worst inputs, the repetitive text with the Pizzascili corpus. And actually, you can reach the implementation from the GitHub. So it is for sure that this method will not be very beneficial once once the length of that shortest unique substring is huge. So we would like to see the SUS coverage. What I mean is, for example, when we do a sampling with 32, which is the default parameter in the SDSL platform, and we counted how many of the positions on the text has a corresponding SUS less than or equal to 32. So it is 93. 6% on the DNA case, and on the average SUS length is that much. So we see that actually for the DNA sequence, the coverage seems nice. For the DBLP, it is poor on the small sampling factors, but more or less on high sampling rates, the coverage is not that much bad. This means that actually we will be happy with that much of the positions for 99 or 90, 96 or 99 percentage of the positions. So on the experiments, what we do is among these positions, we did one basic benchmark. So if we have created an FM index on the reverse text separately, and again with a sampling ratio for 32, 64, and 186, 128, so we will be able to extract these suffix arrays with some time. So what we are doing is we are not using that space. Instead, we are using it from the forward elements. So how much that is slow when compared to the original one? So we see that actually we consider mostly the DNA sequences, and so the sampling of the suffix arrays are two-phase suffix order and text order, and we usually, this is mostly used in practice, so let's focus on the suffix ordered case. On the suffix ordered case, the proposed thing is 2 times 7 slower than the regular FM index for the reverse suffix array. On the inverse suffix array, the default parameter in SDSL is 64, and now we are 3.2 times slower. So this, on the average, if we look to the other results, we just roughly can say that we are 2 to 3 times slower than a regular FM index access with some sampling strategy. But in return, we are not using any additional space. And what is more, actually this speed up is totally dependent on the length of that shortest unique substring. So sometimes we are 1 to 2 times slower, and sometimes it is bigger. So we also included a diffraction of the slowdown here. And interestingly, at some points, even it is possible that this method behaves faster than an original FM index. So initially, we also thought that how can this be? Because in the original algorithms we are doing, we also refer to the suffix array and the inverse suffix array of the forward text. But the reason is this: if the time we spend on the SUS extraction and suffix array access on the forward index might be sometimes smaller than the suffix array access on the reverse index. You can find the discussion related to that in the paper as well. So I guess my time is over. So I would like to finish it with some future directions. First of all, we need to handle those positions with long SUSs. One thing is, so these are not much. So let's say 5%, 4%, something like that for the DNA sequences, and maybe we can just compile them separately. But maybe there might be better methods to achieve it. And the second thing is, there can be some applications on read mapping. So, for example, for the reference genome, computing the Burrows-Wheeler transform of a reference genome. As we mentioned, what we do currently is we augment the original sequence with the reverse complement. Instead of it, is it possible that we do not make this augmentation but still can perform fast pattern matching in the reverse direction using the forward elements? And another thing is surely that parallel construction of the Burrows-Wheeler transform for the reverse text. So since every position can be computed without any dependency. So that's embarrassingly parallel. So which means that with n processors, you can compute it in constant time, something like that. So thanks for listening me. So if you have any questions, you can ask, or you can just drop me an email, however you want. Thank you.